Okay guys, so this is problem 2.14 out of Griffith's Introduction to Electrodynamics. Before we get into this problem, I just wanted to ask if you would please like the video and subscribe to the channel. I'm trying to grow the channel and I'd really appreciate it. Things have been pretty busy with grad school and everything, but I'm still hoping to stay pretty active on YouTube and upload at least once a week or so. So let's start problem 2.14. It says find the electric field inside a sphere that contains a charge density proportional to the distance from the origin, rho equals k times r, where k is some constant. Okay, so I tried to draw a little bit of a picture here. You have this big sphere r, and then we have this Gaussian sphere of radius little r inside of it. And the charge density increases the further away from the origin you get. So I kind of try to represent that with some of these lines. Out here it would be maybe more dense, and then over here kind of dense, and then out here not really. So hopefully you get the picture. And our goal is to find the electric field. So clearly this is going to be a Gauss's law problem. We have one of the symmetries that is helpful with Gauss's law, spherical symmetry. So we'll use Gauss's law. And on the left side of the equation, it's pretty straightforward. It'll just be the magnitude of your electric field times 4 pi little r squared. Remember that dA is coming from a little chunk of the sphere here. That's that surface area that we are including. And this is going to be equal to Q enclosed over epsilon naught. So far so good. But what is Q enclosed? Well, we don't really know. If all the charge was on the outside on the surface of the sphere, well, we would know the electric field is 0, and when we look outside of the sphere, well, we're looking at all the charge. But it's a little bit different here because the charge changes the further away you are. So what we're going to say is that Q is equal to the integral of dQ, where we add up all the little chunks of charge, and that'll be your total charge. Now dQ, the total charge, can be thought of as the charge density, the charge per volume, times d tau, which is some volume element. That makes sense. Charge equals charge per volume times volume. And that's what we're going to substitute into this integral. Q is the integral. Now this will be a triple integral because it's a three-dimensional problem. Rho was k times r, so I'm just going to factor an r out. We have a factor r. And then for the d tau, again, this is spherical symmetry, or this is a spherical integral, so we'll use r squared sine theta dr d theta d phi. And our bounds will go from 0 to r, so technically you might want to make these r's prime notation so that they're dummy variables. We'll integrate from 0 to pi for theta and 0 to 2 pi for phi. So this is a pretty simple integral to do. The integral from 0 to pi of sine of theta d theta is negative cosine theta. I know I've done this before on the channel, but there's a lot of new people now. The semester just started, so I figured this is worth doing. Just again, always good practice. So if you evaluate this integral, this is negative 1, this part is 1, so negative 1 minus 1 is negative 2, and then the negative sign, that's 2. And obviously if you integrate d phi from 0 to 2 pi, that'll just be 2 pi. So then Q is equal to 4 pi times k times the integral from 0 to r r cubed dr. Once again, pretty simple integral. You'll get pi k r to the fourth. And this is really your enclosed charge. This is the enclosed charge from 0 to r. So now what we can say is that the magnitude of our electric field times 4 pi r squared, remember, that's what we just got from up here, is equal to the enclosed charge, which we just found to be pi k r to the fourth, and then we divide by the epsilon naught that's in Gauss's law. Now we can divide, we can see clearly the 4 pi's will drop, 2 of the r squares will drop, and then your electric field as a function of r is going to be k r squared over 4 epsilon naught in the r hat direction. So hopefully that makes sense. If it did, please like this video and subscribe, and I'll post more videos soon. Thank you.